Most of the transmission line problems involve the use of complicated equations. The solution of such problems is tedious and difficult because the accurate manipulation of equations is necessary. To simplify their solutions, we need a graphic method of arriving at a quick answer. The popular chart is developed by Philip H. Smith known as Smith chart. The chart consists of a plot of the normalized impedance or admittance with angle and magnitude of a generalized complex reflection coefficient in unity circle. That graphic aid, somewhat modified over time, is still in constant use in microwave electronics and other fields where complex impedances and transmission line problems are found. The Smith chart is indeed a powerful tool for the RF designer. The modern Smith chart is shown in figure and consists of a series of overlapping or orthogonal circles, that is, circles that intersect each other at right angles. The set of orthogonal circles makes up the basic structure of the Smith chart. A baseline or center horizontal axis is highlighted in this figure and it bisects the Smith chart outer circle. This line or horizontal axis is called the pure resistance line and it forms the reference for measurements made on the chart. A complex impedance contains both resistance and reactance and is expressed in the mathematical form Z is equal to R plus or minus J X ohm. Z the complex impedance, R the resistive component of the impedance, X the reactive component of the impedance. The pure resistance line represents the situation where X is equal to 0 and the impedance is therefore equal to the resistive component only. In order to make the Smith chart universal, the impedances along the pure resistance line are normalized with reference to system impedance. For most microwave RF systems, the system impedance is standardized at 50 ohm. To normalize the actual impedance, divide it by the system impedance. For example, load impedance is given in ohm. The normalized impedance is calculated by dividing the given complex impedance by system impedance, which is in the form R plus or minus J X. Normalized impedance is dimensionless. The pure resistance line is structured such that the system standard impedance is in the center of the chart and has normalized value of 1.0. This is the center of the chart, denoted as O. This value derives from Z0 divided by Z0, which is equal to 1.0. To the left of the 1.0 point are decimal fraction values used to denote impedances less than the system impedance. Similarly, points to the right of the 1.0 are greater than 1 and denote impedances that are higher than the system impedance. By using normalized impedances, we can use the Smith chart for almost any practical combination of system and load and source impedances, whether resistive, reactive, or complex. Reconversion of the normalized impedance to actual impedance values is done by multiplying the normalized impedance by the system impedance. That is, for example, Z is equal to normalized impedance into system impedance, which is equal to R plus Jx. Resistance circles. Normalized resistances are shown as resistance circles. The normalized resistance of any point is found by following the resistance circle to the horizontal axis and reading of the value. This point is always center of the Smith chart, where VSWR is equal to 1. At this point, VSWR is equal to infinite. At this point, VSWR is equal to 0. On the horizontal axis, we read the resistance circle values. Reactance circles. Reactance axis lies along the circumference of the Smith chart. Values are labeled on the axis. Normalized reactance is shown as reactance curves. The circles above the pure resistance line represent the inductive reactance. The circles below the pure resistance line represent the capacitive reactance. Outer circle parameters. Circle A is the reactance circle. The circle B defines the wavelength distance relative to either the load or generator end of the transmission line. There are two scales on the wavelength circle B, and both have their zero origin on the left hand extreme of the pure resistance line. Both scales represent 1/2 wavelength for one entire revolution and are calibrated from 0 through 0.50 such that these 2 points are identical with each other on the circle. In other words, starting at the 0 point and traveling 360 degrees around the circle brings 1 back to 0, which represents 1/2 wavelength or 0.5 lambda. Although both wavelength scales are of the same magnitude 0 to 0.50, they are opposite in direction. The outer scale is calibrated clockwise and it represents wavelengths toward the generator. The inner scale is calibrated counterclockwise and it represents wavelengths toward the load. These two scales are complementary at all points. Circle C defines the reflection coefficient angle in degrees. The scale starts at 0 degree on the right hand end of the pure resistance line, which corresponds to an infinite resistance, and it goes halfway around the circle to 180 degree at the 0 end of the pure resistance line. The upper half circle is calibrated 0 to plus 180 degree and the bottom half circle is calibrated 0 to minus 180 degree. Reflecting inductive or capacitive reactance situations respectively. Radially scaled parameters. We can determine VSWR using D line. We can determine return loss in decibels on E line. We can determine magnitude of reflection coefficient on F line. And using G line, we can determine transmission coefficient of the transmission line. Characteristics of Smith chart. There are two families of orthogonal circles in the chart, constant R circles and constant X circles. The upper half of the diagram represents plus Jx and lower half of the diagram represents minus Jx. For admittance, the constant R circles become constant G circles and the constant X circles become constant susceptance B circles. On the chart, impedance representing by R plus Jx form and Y is G plus JB form. The distance around the Smith chart once is 1/2 wavelength, that is 0.5 lambda. The horizontal radius to the right of the chart, center corresponds to Vmax, I minimum, Zmax and standing wave ratio. The horizontal axis to the left of the chart center corresponds to V minimum, I max, Z minimum and 1 by standing wave ratio. Consider an example in which system impedance is 50 ohm and the load impedance is 95 plus J55 ohm. Here we will see how to mark the impedance on the Smith chart and how to find out the admittance for that corresponding impedance on the chart. Initially, we have to find out normalized impedance. Normalized impedance is given by given load impedance divided by system impedance, which is equal to 95 plus J 55 ohm divided by 50 ohm, which is equal to 1.9 plus J 1.1 is normalized impedance. Normalized ZL is 1.9 plus J 1.1, which is in the form R plus JX. So in the Smith chart, 1.0 is always center of the Smith chart, name it as O. So here I have to mark R equal to 1.9 resistance circle. This is 1.2, 1.4, 1.6, 1.8 and it's 2. Therefore, my R is equal to 1.9 circle is between the 1.8 and 2. So I can say this is 1.9. So and plus J, that's why I have to move along this circle upward. And now I have to mark the J 1.1. So reactance circle, this is 1.0 and it's 1.2, therefore this is 1.1. So 1.1 reactance circle should coincide with 1.9 R circle. This is a coincide point. Name it as A, and this is normalized ZL 1.9 plus J 1.1. Now draw OA radius. With OA radius, draw the VSWR circle. So now we have marked the ZL on the Smith chart and drawn VSWR circle. Now we have to find out the admittance corresponding to the ZL impedance on the same chart. For that, impedance radius OA extended to the B through the 1.0 center point until it intersects the VSWR circle again. AB line intersects at point B is the admittance point on the Smith chart. It is equal to, so this R circle coincides at the B point and this X circle coincides at B point. So this is point 3, it's point 4, therefore R circle is 0.39 minus j 0.2, 0.3, and it's 0.22, and it's 0.44, and in between 0.22 and 0.24 x circle is 2.23. So normalized admittance is equal to 0.39 minus j 0.23. Therefore, admittance is equal to normalized admittance multiplied with the y naught. Y naught is equal to 1 by z naught. Therefore, y is equal to load admittance for the given problem 0.39 minus j 0.23 divided by 50. Therefore, YL is equal to 0.0078 minus J 0.0046 ohm. This is the answer for the example problem. First problem, given the normalized load impedance ZL is equal to 1 plus J1 and the operating wavelength lambda is equal to 5 cm. Determine the first Vmax and Vminimum from the load and the VSWR. For given problem, I have to solve VSWR and I have to determine the first Vmax and Vminimum from the load end. This is my transmission line, generator, load end. Load impedance value has given, that is 1 plus J1. I can directly mark the 1 plus J1 on the Smith chart since it's a normalized load impedance value. From the load end, when I travel towards the generator, I'll get the Vmax position and then Vminimum position. We can find out VSWR, Vmax and Vminimum position using Smith chart. ZL is equal to 1 plus J1. We know that upper half of the diagram represents plus Jx. Upper half of the diagram represents plus Jx. Firstly, note down the R circle. Then X circle. R is equal to 1. So, in the Smith chart, this is a R circle. R equal to 1 circle. Jx is equal to 1. In the Smith chart, you can see that this is a Jx circle. Jx is equal to 1 circle. And R equal to 1 circle and Jx is equal to 1 circle, R equal to 1 circle and Jx is equal to 1 circle coincides at this point. This is equal to ZL. R equal to 1, X is equal to 1, coincides at this point. Name it as A. This is a ZL position. ZL is equal to 1 plus J1. O is always center of the circle. With O center, radius equal to OA, draw the circle. This circle is called voltage standing wave ratio circle or VSWR circle. It's a VSWR circle. This VSWR circle cuts the central horizontal axis at point B on the right side. At this point, a value of VSWR is read equal to the value of R circle of the chart. R circle of the chart. You can see in your Smith chart, in this figure, the value of VSWR is 2.6. The VSWR circle cuts the center horizontal axis and which coincides with the R circle of the chart. That point is VSWR value, that is 2.6 in this problem. Now the line OA extends to OA dash and intersecting the distance circle. From this point, that is from load end, I have to travel towards the generator to read the first Vmax and the first Vminimum. We can see in your Smith chart, outer circle shows reading in wavelength and the return towards the generator. And arrow is in this, like this. Next circle, this circle shows reading in wavelength towards the load and arrow is like this. In this problem, from load end, I have to travel towards generator. Along with this outer circle to read the first Vmax and first Vminimum value. We know that the horizontal radius to the right of the chart center, horizontal radius to the right of the chart center corresponds to Vmax. The horizontal radius to the left of the chart center corresponds to V minimum. And one circle is equal to 1 circle is 0.5 wavelength. We can see from the chart it starts from 0 and ends at 0.5 lambda values, readings. So to find out first Vmax, I have to travel from the load end, that is A dash, towards the generator till the horizontal radius to the right of the chart center. This is distance from load end to the Vmax position. When we travel towards the generator. Now read the value at this point, that is in my chart it's 0.162 lambda, and read the value at this point in the outer circle, that is 0.25 lambda. Therefore it's 0.25 lambda. Therefore distance between Vmax, distance from load end to the Vmax is 0.25 minus 0.162 lambda. Now I have to find out V minimum position. For the V minimum position, I have to travel from the load end to the V minimum position, that is towards the generator. From the load end towards the generator, if I travel towards the generator, I'll get the distance between the load to the Vmax position that is dV minimum. So dV minimum, I have to note down the value at this point and I have to note down the value at this point by considering the outer circle readings. When I travel from load end to the generator end, from load end to till the horizontal radius to the left side of the chart center, which corresponds to V minimum, I'll get the distance of V minimum is equal to, here the reading is 0.5 minus, here reading is in my chart reading is 0.162 in wavelength. At load end position from your Smith chart, when we consider the outer circle, we can read the value at this point is 0.162. At this point, reading in outer circle is 0.25. At this point, reading in outer circle is 0.5, and we have to consider the outer circle for this problem since we are traveling from load end towards the generator end, and we need to consider the distance reading of the Smith chart in wavelength. Therefore, distance between load end to Vmax position is 0.25 minus 0.162 lambda. And distance between load end from load end to V minimum position is 0.5 lambda minus 0.162 lambda. We will find out the value of the distance between the load end from load end to V max position and from load end to V minimum position in the next slide. Therefore, distance from load to V max position is 0.25 minus 0.162 into lambda, which is equal to 0.088 multiplied with lambda 5 centimeter, which is equal to 0.44 centimeter. Distance between load and V minimum position is 0.5 lambda minus 0.162 lambda, which is equal to 0.338 multiplied with the lambda values 5 centimeter, which is equal to 1.69 centimeter. For given problem, when we find the solution through the Smith chart, VSWR is 2.6 and this is given transmission line problem. Generator is connected and load end. Load ZL is equal to 1 plus J1 and lambda is given, it's 5 centimeter. From the load end, when we travel towards the generator, we will get the Vmax position and V minimum position, and from the Smith chart, after solving the given problem, we got the dV max is equal to 0.44 centimeter and we got V minimum distance between load and V minimum position is 1.69 centimeter. Second problem, a transmission line with a characteristic impedance 50 plus J0 ohm is terminated in an impedance 25 minus J100 ohm. Determine the voltage reflection coefficient at the terminal load end of the line using Smith chart. Given Z0 is equal to 50 plus J0 ohm, ZL is equal to 25 minus J100 ohm. We have to normalize the load impedance. Therefore, divide the given ZL value by characteristic impedance, which is equal to 25 minus J100 ohm divided by 50 ohm, which is equal to normalized load impedance is 0.5 minus J2, which is in the form R minus Jx. Now we can mark this value in the Smith chart. Normalized load impedance for given problem is 0.5 minus J2, which is equal to R minus Jx. We know that lower half of the diagram represents minus Jx. Now note down R equal to 0.5 circle. R equal to 0.5 circle. Read the R circle values on the center horizontal line, where we will get 0.5 circle is this. This is 0.5 circle. And it should coincide with minus J2 line. That's why I traveled downwards. And my 2 is here, minus 2 is here. Therefore, I have to travel on this minus x minus 2x circle, and this is ZL point. This is, name it as A, and its ZL, which is equal to 0.5 minus J2. R equal to 0.5 circle, 0.5 circle, and minus Jx is equal to minus J2 circle coincides at point A, which is equal to 0.5 minus J2. O is always the center of the Smith chart. Now consider the OA radius and draw the Vswr circle. This Vswr circle cuts the central horizontal axis at point B on the right side of the chart. At this point, the value of rho or Vswr is 10. You can read in your Smith chart. With O as center, radius OA and arc DE cuts the reflection coefficient line. This is a reflection coefficient line. It's written here, reflection coefficient line. Let this intersection point be F. At point F, the value of reflection coefficient is equal to 0.82. See, reflection coefficient line here, it's here. You can read 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.82. The line OA is extended up to A dash and intersecting the outer scale. The angle corresponding to OA dash gives the reflection coefficient angle. In the third circle, this circle shows the reading in degrees corresponding to angle of reflection coefficient. Angle of reflection coefficient. The line OA extended up to A dash. The angle corresponding to C gives the phase angle of reflection coefficient. At point C, the value of the phase angle is minus 51 degree. Therefore, reflection coefficient is 0.82 angle minus 51 degree. This is the answer for the second problem. Third problem. Suppose that the characteristic impedance of the line R0 is 50 ohm and the SWR is equal to 2 when the line is loaded. When the load is shorted, the minimum shift 0.15 lambda toward the load. Determine the load impedance. If this is a transmission line, source is connected and load is connected at the load end. Somewhere between the transmission line, we will get the V minimum position. When the load is shorted, then the distance between V minimum location and the load is 0.15 lambda. Then I have to find out load impedance. From the V minimum position, first V minimum position, if I travel towards the load, I'll get the ZL value. We will solve this using Smith chart. SWR is equal to 2. It's given in the problem. Plot the SWR circle for rho is equal to 2. We know that the horizontal radius to the right of the chart center corresponds to rho. The value of SWR is equal to 2 is read equal to the value R at point B. Here R equal to 2 on the chart. 1.0 is always center of the chart. Consider OB radius Draw the SWR circle for rho equal to 2. We know that the horizontal radius to the left of the chart center corresponds to V minimum. It's given in the problem that distance between V minimum and ZL is 0.15 lambda. Move a distance of 0.15 lambda from the minimum point along the distance scale towards the load and stop at 0.15 lambda. From the V minimum position to the load position, distance is 0.15 lambda. Travel from V minimum position towards the load for 0.15 lambda. Note down the 0.15 on the second circle of the chart. Draw a line from 0.15 lambda point to the center of the chart. The intersection between the line and the SWR circle is ZL. This R circle coincides with this point, and this JX circle coincides with ZL point. This R circle equal to 1 and Jx is minus 0.65 is normalized load impedance. Therefore, ZL is equal to normalized load impedance multiplied with the Z0 is equal to 1 minus J 0.65. Z0 is given in the problem, that is 50. Therefore, ZL is equal to 50 minus J 32.5 ohm is the answer for the third problem. Fourth problem, determine the length of short-circuited stub having characteristic impedance 200 ohm and source impedance minus J100 ohm using Smith chart. Given transmission line connected generator and connected the load. This is a short circuit point. Distance between short circuit point and to the generator is length of the transmission line. So length of the transmission line we can find out using Smith chart. Z0 is given in the problem. Z0 is equal to 200 ohm. Zs is equal to minus J 100 ohm. Normalized value of input impedance is Zs is equal to given source impedance divided by characteristic impedance, which is equal to minus J 100 ohm divided by 200 ohm. Therefore, normalized source impedance is equal to minus J 0.5. R minus, it is in the R minus Jx form, which is equal to 0 minus J 0.5. Now, R is equal to 0. So, R is equal to 0 here. Minus J 0.5. Lower half of the chart shows the minus Jx. Therefore, minus 0.5, it's here in the Smith chart. This is a source impedance position is 0.J.5. We know that 1.0 is always center of the chart. OA radius, draw the circle. This is a Vswr circle. Extend the OA to OA dash. Always this position is short circuit point and the right side of the horizontal axis is open circuit point. From the point of short circuit, the number of wavelengths up to point A dash is measured moving in a clockwise direction along the periphery of the chart. From the short circuit point towards the generator. From the short circuit point towards the generator till A dash line, when we move from SC, it coincides the line at this point. The value of that point is 0.42 wavelength, which is equal to length of the transmission line. It's the answer for the fourth problem.